Hello all and welcome to today's webinar. It's the first of many within the product lifecycle series. And what better way to start than with raw materials? Today's webinar is titled Bioplastics Technology and Markets Overview of Drivers, Development and Trends. I am now joined by the wonderful Dr. Terence Cooper, who will be presenting this webinar. Dr. Terence is the CEO of Argo Group International, which provides specialised consulting services in chemicals, polymer science, materials technology, market and applications developments, as well as strategic analysis in North America, Europe and Japan. As ever, I'd like to remind you that this webinar is being recorded with a copy of the slides being available to you shortly on the BPF website. If you have any questions during this presentation, please send them via the chat box in the GoToWebinar control panel for myself and Dr. Terence to go through at the end. So without further ado, over to you, Dr. Terence.
Hi, good morning. Morning my time. What I want to do today is give you an overview of the status and the developments of bioplastics technology and markets. So we'll talk about some basic definitions and classifications for bioplastics, feedstocks and the concept of platform chemicals, and then some commercial and developmental bio-based plastics and biodegradable plastics, current markets and applications, and some green issues and consumer and environmental concerns. So what is a bioplastic? Well, this term, it refers to plastics which are bio-based or biodegradable or both of these. So it includes bio-based plastics such as they're not necessarily biodegradable. They may simply be conventional polymers like polyethylene and PET, but made from renewably sourced monomers rather than from petrochemicals. They could be plastics containing both petroleum-based and bio-based monomers, such as PET, where you have more than one monomer, and again, not necessarily biodegradable. Then they can be biodegradable or compostable plastics derived from bio-based materials. They could be natural materials like starch or cellulose, or synthetics like polylactides, polyhydroxyalkanoates. And finally, they could be biodegradable or compostable materials which are actually petroleum-based, even though they're biodegradable. So that would include, say, polybutylene adipate terephthalate and polycaprolactone. So the classifications of bioplastics, two major divisions then, bio-based renewable plastics, and the US Department of Agriculture definition for this, organic plastics composed wholly or significantly of recently fixed new carbon from biological sources. And this is shown by the carbon-14 content. These are renewable within 1 to 2 years versus millions of years for petrochemicals. And the focus is only, totally, solely on the origin of the carbon constituents, nothing else. So these can be fully or partially bio-based. They could be biodegradable or they could be non-biodegradable. The other big division is biodegradable and compostable plastics. So here the focus is only on the end of life process, nothing to do with the carbon sources. And biodegradability is determined only by the polymer structure. So these can be bio-based or they can be petroleum-based. So notice that these two classifications are not mutually exclusive, and bio-based does not necessarily mean biodegradable, and biodegradable does not necessarily mean bio-based. I want to emphasize that because there's a lot of confusion about this. Maybe a little easier to see this, the green ones at the top here, these are bio-based materials. The blue ones down the right-hand side are biodegradable materials. And this top right-hand corner here, this quadrant, are both bio-based and biodegradable. And the bottom left quadrant is neither bio-based nor biodegradable. That's the conventional petroleum-based plastics. So why do we need bioplastics? What's driving it? Well, first of all, Government and consumer and non-government organization demands to reduce dependence on fossil feedstocks and convert to greener materials. Regulatory and consumer concerns over carbon footprint and greenhouse gas reduction, about ocean pollution, single-use plastics, circular economy, all of these feed in to drive bioplastics. Increasing legislation and regulations restricting uses and disposal of petrochemical plastics and promoting bioplastics. Advances in a whole range of thermocatalytic and microbiological processes for converting renewable feedstocks and biomass to bio-based materials. And finally, renewables are increasingly becoming to be seen as a fundamental pillar of a coming bioeconomy where biological sources produce energy, chemicals, and materials with a lower carbon footprint. So governments are leading this. There's the European Commission Lead Market Initiative, a new bioeconomy strategy to scale up the use of renewable resources, build biorefineries. They're providing some seed funding, standards, labeling, certifications, and legislation promoting market development and green public procurement towards the circular economy process. In the US, there's the US Department of Agriculture Certified Bio-Based Product Labeling Program. You can see the kind of logo that's given there. It needs a minimum of 25% new carbon, and that also makes products eligible for the Biopreferred program for procurement by government contractors and government departments. How do we know something's bio-based? Well, there are two major certification programs. There's TÜV in Austria with the, you see the logo at the top there, and this has different ranges, and that would be denoted by stars above in the green panel there. The DIN CERTCO program in Germany again has different ranges, and that's put into the logo. There is no equivalent certification system yet in the US to this. What are bio-based plastics made from? Well, the feedstocks come in essentially four different types. First of all, agricultural food crops and byproducts and waste. Now, these could be used for human or animal consumption, like saccharides and fats and oils and proteins. But here we get into the food versus fuels and materials controversy. Should we be using these types of crop for making materials and fuels rather than as food crops? The second group is non-food crops. These would be lignocellulosics and cellulosics, and now even algae, which are not consumable, but can be turned into bioplastics. And here we get into the land use controversy. Should we be using land resources for this when we could grow food crops on them? Third division is non-food waste, agricultural and municipal and industrial waste. And fourthly, chemical feedstocks, such as biomethane and carbon dioxide. And there's a whole range of processes, thermocatalytic and microbiological now, to convert these all into plant sugars and syngas and hydrocarbons and downstream chemicals to make bioplastics. Very important concept of platform chemicals. If you're going to make a bio-based material or renewably sourced material, only the first chemical or monomer in the synthesis chain needs to be made from a renewably sourced feedstock. All of the later synthetic steps can be performed using standard chemical processes already developed many years ago, many of them, for petrochemicals. So here's a very simple example. Bioethanol made from fermentation of starches or sugars and so on. Fermentation process is bio-based process, making ethanol, which is now our platform chemical. And now we can use standard chemistry to convert this platform chemical into bio-based ethylene and downstream into all of these other products like polyethylene and so on. Another example, taking biomass and converting it into isobutanol by fermentation processes. This is now our platform chemical, the isobutanol, and we can use standard chemistry that's been around for a long time to convert this to isobutane, and then all of these other products, which now become bio-based because the isobutanol was bio-based. One I want to point out is conversion of paraxylene and then terephthalic acid to make PET. So what's available on the market now? Commercial and bio-based, non-biodegradable plastics. First of all, polyolefins. Ethylene can be made by, bioethylene can be made by essentially two routes, one from bioethanol and the other from bio-based naphtha by thermocatalytic processes. To make ethylene, ethylene is ethylene, and it can then be polymerized into polyethylene, or it can be made in EVA or PVC. There's also now the availability of bio-based propylene from waste oils and fats, which leads to bio-based polypropylene. Polyesters, there's the polyethylene terephthalate plant bottle from Coca-Cola, which is 30% bio-based. There's polytrimethylene terephthalate, Sorona, and even some high temperature polyesters like the isosorbide terephthalate, which are bio-based. There's a whole range of polyamides which are available bio-based. Many of them actually cannot be made petrochemically, but they are available bio-based. And copolymers like polyether block amides and copolyester ethers. Polycarbonates, also isosorbide-based, bio-based ones are becoming available, and polyurethanes, which are partially bio-based using soy-based polyols, or even carbon dioxide-based polyols now, and also isocyanates, which are isosorbide-based. There's a lot of developmental polymers coming along, totally bio-based PET and polyethylene furanoate, for example. So who's making these? The companies involved here is like a roll call of the chemical industry. Most large chemical and petrochemical companies are involved, with a lot of small companies and startups. A key factor here is partnering of groups of companies to put together their technology and market knowledge. And I'm not going to go through all these in detail, but you can see the kinds of companies involved with polyolefins and polyesters and polyamides and so on. Let's talk specifically now about some polyethylene, green polyethylene. This started off in Brazil in 2010. There's high density, low density, and linear low density available. And these are identical to the petrochemically made polyethylene, as long as they're made by the same polymerization process. The green polyethylene is recyclable the same way as petroleum-based PE. It right now is higher cost because of the low price of oil and gas right now. Ethylene's low price, and also there's a 40% mass loss when ethanol is converted to ethylene. The big advantage is the huge carbon negative footprint and global warming potential compared to bio-based, petro-based ethylene. So it has very, very substantial green marketing credentials, and many big companies are using these materials, particularly for packaging, as you can see there. Here's some examples. It can be used for anything that ethylene, petro-based ethylene is used for now: rigid packaging, flexible packaging, injection molding, and so on. Here's an example of the Tetra Pak Tetra Rex container, which uses LDPE and HDPE and also a paper component. And that's I'm Green is the Braskem kind of trademark on this. Moving on from PE, partially bio-based PET. This is the Coca-Cola plant bottle, which I'm sure you've all seen. And also Heinz are using it now for their tomato ketchup packaging. What is partially bio-based PET? This is where one of the monomers, the ethylene glycol component, is replaced by a bio-based ethylene glycol that's commercially available. So it's now about 30% by weight bio-based. A lot of active development now to make the terephthalic acid moiety bio-based so that we can have 100% bio-based PET. So how do we make bio-based terephthalic acid? If you make it petrochemically, most of the routes go through paraxylene, which is oxidized to terephthalic acid, and hence the PET. So many of the bio-based routes go through that kind of procedure as well. GEVO that we talked about before, from isobutanol to paraxylene, Virant, together with Johnson Matthey and BP and Torre, a chemical catalytic process to go to paraxylene. Anelitech, also working with Johnson Matthey, catalytic process to aromatics. BTX, benzene toluene xylenes, which is what you get out of the petrochemical process as well. Origin in California, a little different, where they're fermenting cellulosics to go to furanics, and then from there to paraxylene. And BioBTX, a startup in the Netherlands, catalytic process from glycerol again, to make terephthalic acid eventually. So the competitiveness, the economic competitiveness of these kinds of process depends very much on oil and naphtha prices to make oil and naphtha petroleum prices. Because it's quite difficult to compete with all these kinds of processes, the most commercially, the one that's closest to commercialization now is the Anelitech process, which is catalyzed fluid bed process to make BTX. They've been running a pilot plant in Texas now for many, many hours. They're building a 40,000 ton per annum demonstration plant to go from loblolly pine from Georgia to BTX. And they're going to use the data from this to scale up to about 250,000 tons per annum. They claim their process is cost competitive, so it'll be interesting to see how that works out, but with a very marked reduction in greenhouse gas emissions. And the BTX product has been converted by two other partners in this project in France to high purity paraxylene and terephthalic acid. And you can also make the BTX to make other types of polymer. Because of the economic constraints making terephthalic acid, some other companies have gone a different route using furane chemistry. The most important ones probably are Avantium and Corbion, and they are making not terephthalic acid, but furan dicarboxylic acid, this molecule here, as a replacement for terephthalic acid. And the economics to make the furan dicarboxylic acid are much better than making terephthalic acid. You don't have to add hydrogen. You need much less mass of feedstock. And when you polymerize it, you get polyethylene furanoate, which has better properties than polyethylene terephthalate. So you can see that here. It has a higher heat distortion temperature. It's easier to process because it actually has a lower melt temperature, higher modulus and tensile. But a real big advantage is order of magnitude improvement in the oxygen and carbon dioxide barrier, and a significant improvement in the water vapor barrier. And these can be improved further by metallization and vapor coating and orientation. If you use bio-based ethylene glycol, it's 100% bio-based. And for recycling, you can separate it out from PET by near-infrared scanning. So Avantium right now, they have a pilot plant in the Netherlands. They're working with Coca-Cola and Danone on packaging, with Alpaworks on molding. They have partnerships with Mitsui and Toyoba, and they're part of the EU Preference project, with the aim of which is to use furan dicarboxylic acid for a wide variety of different polymers. to make them bio-based. They have an initial plant under construction in Europe, demonstration plant, 5,000 tons per annum, and they'll use the data from this to scale up to 150,000 tons per annum. They've developed improved polymerization technology to give very high molecular weights and very low color and good thermal stability, and they're focusing now on high-value applications. Let's switch gears a bit. I'll talk a little bit about bio-based engineering resins, commercially available ones, polytrimethylene terephthalate, the DuPont Sorona material. Large applications here are carpet fibers, of course, but also being used for bio-based engineering resins using bio-based 1,3-propanediol as a monomer. Thermoplastic elastomers like copolyether esters, Hytrel and Arnitel Eco, and also block amides, and a whole range, as we mentioned before, of polyamides, which are bio-based, many of which can't be made petrochemically. Just a couple of examples, the DuPont Hytrel thermoplastic elastomer, where the polyether glycols there are replaced by renewably sourced polyether glycols. DSM's EcoPax polyamide for engine covers, and the Zytel 610 bio-based polyamide for Toyota radiator end tanks. I'm going to go now to biodegradable and compostable polymers. What does biodegradable mean? It means it undergoes enzymatic fragmentation and degradation by microorganisms to form water. If it's aerobic, to carbon dioxide, and if it's anaerobic, to methane. The challenge here is it's a very imprecise term. There's no defined criteria or environments or products or time limits. Just because something's biodegradable under one set of conditions doesn't mean it will be under others. Some materials will be biodegrade anaerobically, but they may not biodegrade aerobically, and vice versa. Because of this, some standards were developed for actual compostability, which is an aerobic process, and materials have to meet the specific requirements of these standards for either industrial compostability or home compostability to be called compostable. And certifications for this, important to realize, they cover a product, not just material. So this includes determining the maximum thickness that can be degraded within one composting cycle. You may be able to get a certification, for example, for a thin film, but this doesn't mean that it will also get certification for a 5mm thick injection molding. And using compostable plastics, though, requires almost dedicated infrastructure for collection and sorting and identification and composting. So you have to have the infrastructure to use compostable polymers. Here's some certification logos for industrial composting for EN 13432, which is the standard in Europe, from TUV and DIN in Germany, and also Greenpla in Japan, and ASTM CD6400 in the US, although most of the US testing is actually done by DIN now. For home composting, there's the TUV Austria and the DIN certifications. Home composting and industrial composting are similar, except that the industrial composting certifications carried out at much higher temperature and with a much shorter timescale. So what's available now, biodegradable and compostable? The big one is polylactic acid, which I'm sure most people have heard of. Here, lactic acid, which from the fermentation of starches or sugars or even methane, is now our platform chemical. That's our platform monomer, and that's polymerized by making it into the dilactide, and then ring opening chemical polymerization to get to a high molecular weight PLA. The PLAs are PLA is industrially compostable, but it's not home compostable, and it is not anaerobically biodegrade. It's not generally used unless set to make some films-oriented films. So it's not generally used on its own, but it's used in formulations and compounds to get all kinds of different properties, and also by control of the stereochemistry to get very high temperature properties. Second big group is the polyhydroxyalkanoates, whole family of polymers, the hydroxy butyrate, butyrate valerate, butyrate hexanoate, butyrate oxanoate. These are made not chemically at all, but they're made from starches or fatty acids or even methane again by direct fermentation, which means that the bacteria actually produce this polymer in their bacterial cell structure as the energy storage medium. So a good part of the cost of these materials is how do you extract them from the bacterial cell soup and make them into a material that you can use as a thermoplastic. Because of this, there's an ongoing controversy over whether PHAs are plastic or they're natural polymers. And this is important now because of the Single-Use Plastics Directive, which controls or limits plastics, but not natural products, so polymers, so that, like cellulose, for example. So this is right now in the courts. We'll see how this turns out. A big advantage of the PHA is that they're biodegradable under almost any conditions. They industrially and home compost. They're soil and marine biodegradable. They biodegrade anaerobically and aerobically. But no, the PLAs and the PHAs are both biodegradable and bio-based. So they're different from the kind of drop-in polymers that we've been talking about before, like bio-based polyethylene. Another big group is aliphatic and aliphatic aromatic copolyesters, polybutylene succinate, succinate adipate, adipate terephthalate, caprolactone. These are mostly petroleum-based right now, except for the polybutylene succinate, and they're not usually used on their own. Think of them as rather like low-density polyethylene, and they're used for blending with either polylactic acid or PHAs, or with starch blends, which is the next grouping here. Many starch blends used for packaging or as barrier layers. Cellulose is a very effective barrier layer, and so polyvinyl alcohol and polyglycolic acid, these are water-soluble and biodegradable barrier layers, and polyvinyl alcohol is also used as a blend component with PLA and the copolyesters and with starch blends. Other materials also under development, from protein-based or polysaccharide-based. Who's making these? Well, PLA, this is the big polymer right now. There's about 200,000 tons a year made. NatureWorks in North America, together with PTT, which is a Thai company. Total Corbion have a plant in Thailand. Hysun in Japan. There's actually been a shortage of PLA this year, and Total Corbion are going to be building another plant in Europe, and NatureWorks is expanding its plant in Nebraska. A lot of people are looking to get into the PHA business. The most important ones are Danimer, which has a plant in Winchester, Kentucky. They just opened about 7,000 tons a year, and they're talking about doubling that. And Kanaka in Japan, about a 5,000 ton a year plant, and they are thinking of building another plant in Germany. So all kinds of startup and small companies getting into that as well. I'm not going through all these in detail, but PBAT, a third big component. major producers, BASF, and there's now a couple of Chinese companies. PBS, polybutylene succinate, is available bio-based now from PTT Mitsubishi in Thailand. So what do you use a compostable plastic for? Why do we need them? Well, they're a significant benefit for applications where you're going to have food contamination. And this can be packaging, it can be food service, waste bags, all this, where if you're going to compost the food waste, you can compost the packaging or food service along with it. It's also significant where you can have easy collection and segregation. And I suppose a good example of that would have been the London Olympics a few years ago, or where there's various tax incentives or legal constraints, like in France or Italy, where the materials to be used in, say, food service have to be both biodegradable and bio-based. It's they're used in mulch films, and also now for 3D printing filaments. But you do have to have a dedicated infrastructure. PLA now especially is getting into durable applications, nothing to do with whether it's compostable, for electronic and household and consumer, even automotive applications. And there it's often blended with other non-bio-based and non-biodegradable polymers like PMMA and polycarbonate. Here's some applications for PLA. You can see rigid packaging, flexible packaging, food service ware, fibers, and all kinds of durable products. PHAs, as I said, a whole family of products, and their properties go everything from pressure sensitive adhesive type polymers all the way up to polyethylene and polypropylene, high density polyethylene and polypropylene. And here's an example that Danimer, for example, is working with Nestle and with PepsiCo, and now they've just started working with Bacardi to make biodegradable blow moldy bottles. Here's some starch blend applications. You can see food service as well as flexible packaging and net packaging. And finally, final examples, stand-up pouch for quinoa. This one is a combination of Futamura Nature Flex cellulose as a very good barrier, and Novamont Matabi starch blend. So let's talk about markets now. The Achilles heel of all of these bio-based and biodegradable products is price. And you can see here, these are ballpark figures, but they give you a good idea that these are very expensive compared to standard petrochemical products, which are down here on the right. The cheapest is just the lowest grade of PLA, and even that's only within spitting distance. And that's for the very lowest property ones, which have very low heat distortion temperatures. Bio-based PE and PET are also, you can see here, more expensive than the petrochemical equivalents. So this is something that is retarding the growth of bioplastics. And with the low prices right now for oil and natural gas, this is likely to change anytime soon. But Nova Institute in Germany and European Bioplastics put out projections every year. This is for bio-based plastics. They're projecting next year 4% growth. You can see the big growth they're projecting for polypropylene here. And for biodegradable, they're projecting about a 3.4% low growth. And a large part of the growth here is polyhydroxyalkanoate. So an overall growth of about 3% per annum. This is over a 5-year period from 2019 to 2024. Looking at market segments, they're looking for big growth for flexible packaging, and interestingly, also for consumer goods. You can see this 166 here going up to 239. for consumer goods. And I'm not going to go through all this in detail, but you'll be able to look at them afterwards on the slides. Where are they being made? Well, the major growth, the major production has been in Asia, but over the next 5 years, they're predicting a very large growth in production in Europe, going from 25% of the total up to 30%, whereas everybody else is reducing in percentage terms, although going up in absolute terms. So what are the factors restraining bioplastics growth? First of all, the high price compared to current virgin petrochemical polymer prices. Secondly, the low value of what's called the green premium. Consumers say they want sustainable products, but how much extra are they willing to pay for them? According to a McKinsey study a few years ago, it was about 5%. That may have increased by now, but it's still not very big. Thirdly, when biodegradable and compostable plastics first came onto the market, first of all, they need different process conditions, but they were inferior products at that time. And during the last 10 years or so, all kinds of compounding and stereochemical control technologies have been developed to make them very good products today. But the thought of that still lingers. There's a major challenge in going from proof of concept to industrial scale production. The well-known valley of death for startups. Quite a few small companies have gone out of business trying to go over that with bioplastics. There's a high financial risk in setting up a new industry competing against depreciated petrochemical assets. Paradoxically, improved recycling technologies and setting up more recycling infrastructure for fossil-based plastics, this is likely to reduce the demand for new virgin fossil-based plastics, and because of that, is also likely to reduce bioplastics demand. So consequently, bioplastics are still growing, but only at about the general plastics growth rate. And they're going to maintain a market share of somewhat less than 1% over the next 5 years. Other concerns with bioplastics, first of all, as we discussed before, the use of foodstuff feedstocks. So most work now is aimed at non-food biomass or waste to avoid competition with foods. The availability of land and water and competition for these with foodstuffs and other uses. Whether bioplastics really do have lower carbon footprints than petroleum-based materials, given the agricultural and fuel inputs, and this has to be shown by life cycle assessments, which are usually quite positive in this regard. So not all polymer and chemical production will become bio-based. And bioplastics will only be successful if equal product functionality is delivered at a lower cost, new functionality is provided at the right price, or the carbon footprint's improved. So to sum up, the future growth of bioplastics is going to depend on future trends in oil and natural gas prices, on continuing transition from petroleum to bio-based feedstocks, and improvements in pricing, carbon footprint, and performance, on the development of economic routes from non-food feedstocks to either bio-based polymers identical to the petroleum versions as drop-ins for existing processes and infrastructure and manufacturing processes, or development of new bio-based polymers from non-food feedstocks. Whether there's going to be, as it almost certainly is, a continuing increase in legislation enforcing the use of renewable and or biodegradable plastic materials and restricting petropolymers, whether the green premium remains as low as it is or if it increases, and finally, how well bioplastics address future environmental, societal, political, legislative, and economic issues, not just technological factors. So with that, I'd like to thank you for your interest. I'd like to thank the British Plastics Federation for the opportunity to give this talk, and also Miami Mansour and Dr. Robin Kent from the for the mechanics of putting it on. So with that, I'd be happy to try to answer any questions.
Excellent. Thank you very much, Dr. Terence, for your time and for your very insightful presentation. I'm sure there's been plenty of actionable takeaways that the listeners are going to take on board. While you're presenting, we did have a couple of questions come in. So if I can start with the first, do we have enough sustainable natural resources to switch to 100% bio-based plastics?
I think the answer to that is definitely yes. By natural resources, you're talking about biomass. There's an enormous amount of biomass available, which could essentially replace petrochemicals. And right now, the challenge is cost. If you're thinking about land use, I'm going to put up a chart for land use here from European bioplastics. And if you look, this is going between 2019 and 2024, but all of this much is used for pasture uses, and this much is used for food and feed for animals. Materials from agricultural materials are this amount here, and biofuels are this little sliver here. And don't forget that biofuels is a much bigger industry right now than bio-based materials or bioplastics. Bioplastics, you can barely see the little sliver that's going to be taking, right? This little bit here. That by 2024, it will be 0.021% of land use and resources. So I hope that answers your question, because there's a great deal of emphasis right now, both in Europe and in North America, on capitalizing on a lot of what you might call unused biomass, and trying to make these into much more used resources for making both biofuels and materials. Did that answer the question?
I'm sure it does, yes. And I've also got a couple more questions, if that's okay. And we've also, by the way, had a bit of feedback from the listeners, all of which have been very, very positive, with regards to excellent presentation. Thank you. And thank you very much for this excellent talk. So we've had two very positive bits of feedback there. So you should be very proud, Dr. Terence. That is awesome. And then we've also, obviously, back to the questions. Is there a problem with using land for bioplastics?
Well, that's what I've just answered there. The answer is no.
Okay, cool.
We're talking about by 2024, 1 million or so hectares, which is 0.021% of the world agricultural area.
Okay, that has answered that question very well. Yeah. Okay, cool. And then another question that we have is, how have PLA homopolymers been improved over the years?
Well, when PLA first came out, it was marketed on the basis that it was compostable. And the whole idea was to replace non-compostable plastics. It turned out the market wasn't, the compostability was not the thing that people were buying their polymers based on. It was the other properties. So these other properties had to, one, be improved. And what happened was PLA had a very low heat distortion temperature. It was difficult at that time to process because it needed totally different processing conditions from polyolefins, for example. And it had its physical properties were poor. So over the last 10 years at least, maybe longer than that, all kinds of compounding technology has been developed to increase the heat distortion temperature, to make it suffered from something in the beginning. It went from a ductile to brittle transition when it went into storage. So the impact properties have been vastly improved. And also there's been a big development of the stereochemistry of the product. It's since lactic acid is stereoisomeric, you can make different forms of the polymer, and by the original polymers were a mixture of the D form and, or not a mixture, but a copolymer of D and L with mostly L, a little bit of D. Now we can make homopolymers, which are all D or all L, which give us much higher heat distortion temperatures. And also you can make a kind of blend of these, which has an incredibly high heat distortion temperature, up near 200 degrees Celsius. The challenge is, of course, the higher you make the heat distortion temperature, the more expensive the polymer is, and the slower it tends to compost. I think I have a chart here. Yeah, you can see here these stereo complexes made from all homopolymer, a blend of homopolymer D and L, which get you up to about 230 Celsius. The original, we were talking about a heat distortion temperature of around 55. You can see the improvements there.
Awesome.
I did mention, if we have time, that PLA is generally used on its own. It's used blended with all these other components. And you can see here, FKUR is a compounder in Germany. There's a whole compounding industry set up for bioplastics now. This is the properties for elongation versus modulus. For polyolefins, PLA's out here. It's very brittle, high stiffness. But by compounding and so on, you can now make all these different types of compounds to give you intermediate properties, whatever you want. And also starch blends come in. Many of those also contain PLA, come into the same area. Also improvements in barrier properties. PLA here is not as good as PET, but you can make it also quite good. So I'll leave that. Did that answer the question you asked there?
Yes, it most definitely did. And we also had a question come in while you were answering that question. And the question was, are your laboratories approved by the certification bodies, as I note you offer testing services?
I don't offer any kind of testing services, but the major test labs in Europe, there's a major test lab in Belgium that a lot of people use, but they are certified by the testing bodies. So TUV and DIN would certify different test labs.
Okay, cool. Yeah, no, I don't know why there was a mix up there. I think someone thought that there was testing services being offered. And then finally, before we finish up, there has been one last question. What will be the end of life process of bio-based and biodegradable plastics?
Well, you notice a lot of the bio-based plastics are what we call drop-ins. Instead of developing a new plastic, companies like Braskem and Indorama, for example, with polyesters, have developed exactly the same plastics we have now from petrochemical sources, but from bio-based monomers. So those plastics, those bioplastics, will be end of life exactly the same way as the petroleum-based plastics. They'll go through the same mechanical or chemical recycling processes. And why did the companies do that rather than coming out with new polymers? It's because there's much less business and financial risk. You've got all of the business infrastructure, the manufacturing infrastructure, the end-of-life infrastructure is already there. If you're going to make a new polymer, like Avantium are doing with polyethylene furanoate, now you have to build all that up. And that takes a long time and a lot of input. We've seen that very strongly with PLA and the PHAs, which are new polymers. PLA, it's taken 20 years to get to where they are now, and a huge investment, billions of dollars. And PHAs have been coming and coming and coming for many years, and finally they just about got here. But developing a totally new polymer is a very arduous process. So, but the biodegradable ones or compostable ones, of course, the end of life process for that is mostly industrial composting. Some of them can be home composted. That depends on how many people are going to have backyard composters or be willing to do their own composting. And of course, there's ones which are the PHAs are also one of the advantages of those is they will biodegrade under many conditions. So if they get into the litter stream, they can biodegrade in soil, they can biodegrade in marine. But the idea is not to get them into the litter stream, but if they do get in, that they will disappear rapidly.
Brilliant stuff. Well, thank you so much again, Dr. Terry. That answers all the questions that we have. Thank you again for being an awesome sport. For those listening, the second webinar within the product lifecycle series is coming up tomorrow. So if testing for biodegradation of plastics and packaging materials sounds like a webinar that you'd be interested in, then please do register by logging on to the Lunch and Learn section of the BPF website. So yeah, I guess that concludes this webinar. I'll be ending this webinar for everybody in a second. Before you go though, again, a major thank you to Dr. Terence and all those that have been listening in. We look forward to working with you again on another webinar next year, Dr. Terence, and I'm sure we'll all be back here again and to see the progression of the whole series. So yeah, so thanks again, and I look forward to talking to you guys again soon. Any final words, Dr. Terry, before we leave?
No, that's it. Thank you very much for all your hard work in putting this on.
Awesome, no worries at all. It's been an absolute pleasure. So yeah, so that's it. I'm going to wind it down now, and I'm just going to close down the thing, and we will catch up later on. Cool, excellent. Cheers, everybody. Bye.